Hello and welcome to this talk about the range of once reinforced random walk in one dimension. My name is Jakob Stiefel and this is joint work with Peter Pavluber, both from University of Freiburg. First of all, what is a once reinforced random walk? It's a random walk where the transition probabilities depend on the past of the process. So initially, every edge is assigned a weight 1, and as soon as the random walk moves along an edge, the weight is changed to a parameter c. And then the transition probabilities depend on these parameters. I will give a precise definition in one dimension because this is the main focus of this presentation. So first we write capital M for the running maximum and lower m for the running minimum of the process. And then we can define once reinforced random walk. We have a parameter c, non-negative. We start in 0, and then we have transition probabilities. If the process is somewhere in between maximum and minimum, then we have probability of one half to move one step up or down. And as soon as the process is at its maximum or minimum, we have a probability proportional to 1 to move to a spot where the walk hasn't been yet, and a probability proportional to c to move it back inside to this area where the walk already has been. And the range of this process is defined as the size of the area where the walk already has been. So it's maximum minus minimum of the process. We will take a closer look at the generalized inverse of the range. So Sk is the first time the range is of size k. We decompose this time into the times ti it takes to increase the range by 1. And we can derive a formula for this times ti. And I will explain this formula using this figure down here. So for example, take a look at this spot here. The range right now is 3. And how long does it take to increase the range by 1? Well, it could happen in the next step. But if not, it moves inside this red area again. And inside the red area, this random walk just behaves like a symmetric Bernoulli walk. So we have to wait until the symmetric Bernoulli walk hits the edge of this red area again. And then we again have the chance to move out. If we move in, we wait again until we hit the edge. And then finally we move out. So we go inside this red area geometrically often. And note that we have shifted geometric distribution, as we could also go inside 0 times. And every time we move inside, we have one step inside, and we have to wait until a symmetric Bernoulli walk hits the edge of this area. And this is the formula we have here. And this formula for the inverse of the range is enough to derive our main result. So capital Rn is the expected range. We rescale the range by square root of n. And then the else moment of this term converges to a constant, and we can split this constant in 2 factors. The first factor depends on L, and the second factor depends on L and C. Okay, first, this factor depending on L and C is given by an integral expression, and this integral expression is decreasing in C, which is not surprising because if we are at the edge of the visited area, then we have a probability of 1 over 1 plus c to move to a new spot, which is decreasing in C. So also the expected range is decreasing in C. And for the first factor, we can give expressions for the first and second moment, for example. And for the first moment, this is square root of 2 over pi. And for the second moment, it's just 1. One more comment on the special case c equal to 1. For c equal to 1, we have a symmetric Bernoulli walk. And of course, we have results on the range on the symmetric Bernoulli walk, and we can replicate these results as special cases of the theorem. And we can verify what we did here. So, for example, if we calculate J1 of 1, this is 2, and we obtain a well-known result about symmetric Bernoulli walks. And we could also do this for the second moment. Let's take a look at the proof. I will present the proof in the special case L equal to 1, so the first moment of the range. The other cases for bigger L are like the proof is the same, but the calculations are a little longer. So step 1 is we calculate generating functions of the expected range. And we will make use of the defining property of generalized inverse, namely that Rn is bigger k if and only if sk is smaller n. And then we can derive a formula for the generating function of the expected range in terms of the generating function of the times sk. In between here, it's just some reordering of sums. And we derive the formula for sk, so we can also derive a formula for the generating function of sk, because this sum here, taking generating function, becomes a product, and the second sum becomes a composition of functions. These factors s here and here come from the 1 plus here and here. Next step is we identify the asymptotic behavior of the generating function. And okay, we know generating function of the expected range is we can express by generating function of sk. Sk we can give in terms of yi and tau I. Yi is just geometric distribution, so we can give an explicit expression for the generating function. And tau I is a hitting time of a symmetric Bernoulli walk. And for symmetric Bernoulli walks, we can also give explicit expressions for generating functions, for example, using martingale techniques and optimal sampling. So we have an explicit expression for the generating function, and we can do some calculations to show that the asymptotic behavior is as follows. We have a constant a times 1 minus s to the power minus 3 over 2. And the constant a pretty much looks like the constant j1 of c we had before. And okay, we have the asymptotic behavior of the generating function of the expected range, and now we want to go back to the expected range itself. And therefore we need a result from a theory called Tauberian theory, and this theorem is usually referred to Hardy and Littlewood. It reads as follows: given a sequence non-negative with a specific asymptotic behavior, and this is just a behavior we had right now, constant times 1 minus x to the power minus alpha, then we obtain a result on the asymptotic behavior of the sum of the sequence. And under some further assumptions on the sequence, we obtain a result on the sequence itself. And now we just have to put the single steps together, and we can do this in the case L equal to 1. So we had alpha equal to 3 over 2 on the last slide. So alpha minus 1 appearing here is 1 over 2. And it remains to calculate the constant here. And if we calculate this, it's just square root of 2 over pi times this constant j1 of c. And we can do the same for higher moments, and also this theorem here is used. Let me give 2 final remarks. So the positive aspect about all this is that we could asymptotically compute all moments of the expected range, which is kind of nice. And we didn't have to use any further technique like, for example, this Tauberian result is also straightforward. The negative aspect is that we were unable to compute even moments of the process itself. So this method worked for the range, but not for the process itself. And of course, another negative aspect is that we had to restrict ourselves to 1 dimension. And the reason for this is that in 1 dimension, this shape of the area where the process has been is easy. It's just the area in between maximum and minimum. If we go to higher dimension, the shape of this area is way more complex, and therefore the transition probabilities are more complex, and we cannot generalize the methods we used here. If you want to look up any further details about this, you can take a look at our paper. Thank you very much for your attention.